Hello. This program looks at the gas metal arc welding process, also known as MIG. We'll be covering the history of the process, its characteristics, the materials that can be joined by it, and the areas of industry where it's used. Other areas covered will include typical equipment required and how to set it up and prepare for welding. The program split into 4 sections, with the first covering the principles of the process, the second its features, then the equipment, and finally the working practices of gas metal arc welding.
Gas metal arc welding has traditionally been known as MIG, metal inert gas, or MAG, metal active gas, depending upon whether the shielding gas used is inert or contains active constituents. The development of arc welding began around 1900, with industrial use slowly expanding over the next decade. It was in 1949 that the Air Reduction Company, now part of the BOC Group, patented the methods and apparatus for gas-shielded metal arc welding in the United States. By this time, the gas metal arc welding process had been developed using an inert shielding gas around a consumable wire core. Initially, the process was used chiefly for welding aluminium alloys, which were difficult to weld using other processes. Then either helium or argon were used as the shielding gas. Except for special applications, the equipment and consumables were too costly for the welding of steel. In the 1950s, the process was marketed by British Oxygen in the UK as the Argonaut process and used for joining a variety of metals, including aluminium alloys, stainless steel, carbon steel, and copper. Depending on the material being welded, the shielding gas used could be argon, carbon dioxide, or a mixture of either carbon dioxide and argon, or argon and oxygen. These years saw a rapid growth in the development of the process, and soon better equipment and consumables were available, so that the process was more economic for the welding of steels. The gas metal arc welding process continues to increase its market share around the world, mainly replacing manual metal arc welding. So why is it becoming more widely used, and for what? First, we must look at how the process works. Gas metal arc welding uses the heat from an arc, which is formed between a consumable filler wire and the workpiece. The arc is shrouded by a shielding gas directed around the arc by the nozzle of the welding torch, and the welding current is transferred to the wire by means of a copper alloy contact tip. The heat of the arc melts the filler wire as it is fed into the weld pool. A wire feed unit feeds the filler wire from a spool through the torch. The wire feed unit is set to a predetermined speed, dependent on the material thickness and joint configuration. The shielding gas is also fed to the work area through the torch. A power source with a direct current DC output is used, with the wire connected to the positive terminal via the contact tip and the workpiece connected to the negative or earth terminal. The characteristics of the gas metal arc welding process depend on the mode of metal transfer from the wire to the workpiece. The modes of metal transfer are dip transfer, globular transfer, spray transfer, and pulse transfer. Dip transfer uses a low arc current which is not capable of melting the filler wire as it feeds towards the workpiece. The wire feeds into the weld pool, which causes a short circuit. This causes the current to rise rapidly, and the wire necks before rupturing and re-establishing the arc. Once again, the wire feeds into the weld pool, and the process is repeated in a relatively regular manner. The low current and addition of relatively cold filler wire mean the heat input is low and limit the size of the weld pool. This makes the dip transfer mode suitable for thin sheet and positional work. Globular transfer occurs at slightly higher currents than dip transfer and can be found when using carbon steel wires with carbon dioxide shielding gas. Large droplets are formed at the end of the wire, which are detached by gravity. Transfer is irregular and unstable, giving rise to large amounts of spatter. Spray transfer occurs at high welding currents, which depend on the wire composition, wire diameter, and shielding gas. The wire melts, forming droplets which are similar to the wire diameter, and these transfer through the arc to the weld pool. This gives a stable arc with low spatter levels. Pulsed transfer uses the spray transfer mode, but at lower average currents than those normally used for spray transfer. This is achieved by using a low background current to maintain an arc. As the current is increased, the tip of the wire melts to form a droplet, which is transferred to the workpiece. This process of high current pulses is then repeated as the wire is fed into the arc. This mode gives excellent arc stability and negligible spatter levels. The main controls to the gas metal arc welding process are the wire feed speed, the arc voltage, and the inductance. The wire feed must match the rate at which the filler wire is melted, and this is related to the weld current. If the arc voltage is set too high or the wire feed speed is too low, then the arc length will become too great and the wire may burn back into the contact tip. If the voltage is too low or the wire feed speed too high, then the filler wire does not melt correctly and short-circuits the arc gap, causing an effect known as stubbing. The inductance is used to control the rate at which the current rises during short-circuiting. A low inductance limits the peak current reached during the short circuit and reduces the amount of spatter. Too high an inductance level may result in difficulties striking the arc, and stubbing may occur. A variant of gas metal arc welding is flux cord arc welding, where the consumable filler wire is tubular, containing a core of metal powder or flux. The power source, wire feed unit, and torch used are the same as for gas metal arc welding. A shielding gas is also used, although in some cases a self-shielded wire can be used. As its name implies, the wire is self-shielding, with the arc being protected by gases generated by the decomposition of the flux. Flux cord wires are available for plain carbon and alloy steels, hard-facing alloys and stainless steel. But why are they used in preference to solid wires? Well, they offer the following advantages: much higher deposition rates compared to manual metal arc welding, and slightly more than using solid wire gas metal arc welding. Alloying additions from the flux core, which affect the weld metal properties and operating characteristics. Slag shielding and support, which can aid vertical or overhead welding. And improved arc stabilization and shielding from the decomposition of the flux constituents. However, flux cord wires have the disadvantage of a much higher cost than solid wires and greater fume formation rate, with more potentially toxic constituents, which must be controlled to comply with health and safety requirements. There are many applications for flux cord wires, which include the joining of thick-section, high-strength steels required for critical applications, high-speed mechanized welding, and high-quality stainless steel process plant. Hard-facing alloys are widely used for chemical plant, earth-moving, mining, quarrying, and agricultural equipment. All modes of transfer, in particular dip and pulse, give low heat inputs when compared to the manual metal arc welding process. This makes gas metal arc welding particularly useful for joining thin sheet or for use in positional work. The process has a high operating efficiency and high duty cycle, which allow it to be used for longer times at greater welding speeds than other welding processes. It also has a high deposition rate compared to manual metal arc welding, allowing more weld to be completed in a given time. If the conditions are set correctly, then no or little spatter will be produced. Compared to manual metal arc welding, there's no slag produced and therefore little after-weld cleaning is required. As we mentioned earlier, the gas metal arc welding process is widely used. But what is it used for? Well, in fact, joining most metals over a wide range of applications. Using the dip transfer mode, the process is ideally suited for joining thin sheet materials, which include car bodies, exhausts, tanks, furniture, heating and ventilation. Dip transfer can also be used for positional work, for items such as pipelines, marine structures and earth-moving equipment. The spray transfer mode is for thicker sections, which cover structural steel, prefabricated structures, large vehicles, cryogenic vessels, and surfacing. Pulse transfer can be used for items such as aluminium boats and cryogenic vessels. These are only a few examples of the wide range of items that can be welded, showing how versatile this welding process is.
Mel is with us now to take us through the equipment and some of the working practices of gas metal arc welding. Mel, first of all, should we start with the power sources?
We've got three machines on display here. This is a high amperage, heavy industrial use machine. We have a smaller power source for lighter industrial work. And in the corner we have a synergic pulse machine.
Right, more about that one later on. Take us through this one first of all. Well, first of all, take us through the components we have here.
The components that you have are the wire feed unit, the power source itself, a gas supply, and a welding torch.
Right. Let's go through the control panel next, if we can.
On the power source itself, you have voltage controls. Here you can select the range of voltage, be it low range or high range, and here you have infinitely variable sliding control of the voltage. This compares with, say, the smaller industrial unit that has a stepped voltage control.
Right.
We have the main power on-off switch. We have a switch here that can select remote control. If you didn't wish to work on the machine itself, but away from the unit, you could have remote control. You have an ammeter and a voltmeter to show the welding parameters. Here we have a burn-back control, which is very useful, particularly when welding aluminium, where you can sometimes have problems at the end of the weld with the wire fusing to the contact tip. This allows the wire to stick out further at the end of the weld.
Okay, fine. And down below where the plugs go?
We have the earth return lead. This completes the electrical circuit back to the machine.
Right.
Here is the power supply up to the wire feed unit, and you can see that you have a choice of two ports to use. This is the inductance control. When you're using dip transfer, the inductance determines the amount of time that the resistance heating is allowed to build up in the wire.
Right.
The lead here supplies the low voltage controls for the wire feed unit, and here is the socket if we were to be using a remote control.
Okay. Right, and the wire feeder?
The wire feed unit, the main control is the wire feed speed or amperage. You also have a button here that allows the wire to be fed through the torch without the welding current being applied to the wire. This is a latch control that allows the trigger to be released with the wire still running if you wish to use that on long seams.
Right.
The gas purge button is important to purge the gas system through the torch before welding. The switch here is for spot timer. Often you will wish to do short spot welds, and you can select the amount of time that the spot is allowed to weld.
Okay, and that's calibrated 1 to 5 seconds.
That's correct.
What about these here?
If you're using very high amperage work, it's quite possible that you'd use a water-cooled torch, and this is the water supply.
Okay, right. Now, what about feeding it through? Let's just turn it to the side. That's it.
We have the reel of wire on the back going into the wire feed unit itself. You can see the wire feed rollers here. In this case, this is a 4-roller system. The wire feed rolls themselves are different for whatever diameter of wire that you're using. Here you have the tensioner screw. This can be adjusted again for the different diameters of wire. It's fed through the outlet guide into the torch at the back.
Right. And we have here the
welding torch itself. So this is the back of the welding torch that will connect to the wire feed unit. Here is the liner where the wire is guided up the inside of the torch, and you have different size liners for the different diameters of wire. You also have different types of liner. This one would be for stainless steel or carbon manganese steel, but here is a nylon liner that you would use on soft wires such as aluminium.
Right.
The other inlets at the back of the torch, the gas is supplied into there, and these two electrical points are for the trigger.
Okay, well let me put that on there while you explain the gun end.
The torch itself, the trigger here allows the wire to be fed through, and also the contact to come in to get the welding current through to the contact tip. The contact tips themselves are different diameters for the different wires, and they fit onto the gas diffuser. You can probably see the small ports here that allow the gas to pass out, and inside the shroud they're projected forward onto the weld. The contact tip itself not only guides the wire into the weld pool, but this is where the current is picked up for the wire.
Right, well with those components it's important obviously not to have any damage on them. What do you do if you do damage them? Is it best to replace them entirely?
If they're damaged, replace with new, yes.
Okay.
The gas shroud itself, you can see we've got two different types here. One is for dip transfer. This allows the contact tip to extend slightly beyond the end of the shroud, so that for low amperage work you have more control. However, on higher amperage work, in spray conditions, you need better gas coverage, so we would use the longer gas shroud there.
Right.
That screws onto the torch itself. And there we should be ready to start welding.
Smashing. Okay, let's move on to the other machine, the more complicated machine over here, and take us through the controls.
Yeah, the machine that we were just looking at is a conventional MIG power source. It's been around for 30 years or so. In the last 10, 15 years, they've developed these synergic pulse machines, synergic being where the amperage and voltage, instead of being operated by two different controls or three different controls in the case of that one, it's all controlled on the one knob. On the front of the machine you will see the output control. So as we increase that, that's increasing amperage and voltage at the same time. And it does this by using the programs that are already in the machine. You select the program here on the wire selector. In this case you can see it's set on 1mm wire stainless steel, but you have different diameters and different materials, mild steel and aluminium. We also need to be able to perhaps trim these conditions from time to time. Particularly if you were welding in position, you might need a much shorter arc length than you would if you were welding in the flat position. And in this case you would use the voltage trim to reduce your arc length.
Right, so in a sense you're customizing what you're using, you're customizing the program.
That's correct, but only by trimming. You're not actually setting the parameters themselves. They're already pre-programmed, but you are allowed to trim the condition. You also have a control here where you can alter the background current if you wish to increase or decrease the background current. The whole process itself is selected on this switch. Here we're selecting pulse MIG. You can see there that we could select standard dip or spray MIG. We could also use manual metal arc or TIG.
Fine. What about the slow wire running?
Slow wire running is particularly useful on higher amperage work, where if the wire is allowed to hit the workpiece before the arc is formed, you may have quite an explosive start. This allows a slower wire feed in until the arc is established, and then you go up to the higher wire feed speed.
Right.
You have the ammeter and the voltmeter, the same as on the other machine. You also have the other two controls that we have here, or the two inlets that we have. Remote control again, if you wish to set conditions away from the power source. And here we have an interface that allows this machine to be connected to a robotic unit.
Okay.
You have the power cables down here, the positive going to the wire feed, and the earth return going back into the negative pole.
Right, all cabled up. What about the wire control? It seems to be slightly different.
The wire feed unit is slightly different to the other one, in that this time you cannot adjust the wire feed speed because that's all being done synergically on the control on the front of the power source. But you still have the same wire feeder, the latch control for the torch, the gas purge, and the spot timer.
Right. So that's the power sources, that's the basic hardware. What about consumables? Let's talk about wire first.
The wire, in this case we have solid wire. This can come in a range of sizes from 0.6mm up to 1.6. We have a bare carbon manganese steel wire here, but often it comes as copper-coated wire, such as the reel that you're holding there. You'll also notice that's a lighter, smaller reel, more useful for that small industrial unit than it is for this larger machine.
Right.
You can also have flux cord wires. These allow you to use larger diameters. It also allows you to use alloying elements that you wouldn't be able to use in a solid wire and be able to draw successfully.
Okay, Mel, thank you very much. Of course, the other main consumable is gases, shielding gases. Let's take a closer look at those.
The shielding gas is important in protecting the molten weld pool from atmospheric contamination to prevent porosity, embrittlement and oxidation of the weld, providing a stable arc to provide good metal transfer, controlling the weld bead profile to give maximum penetration and fuse the weld joint, and also controlling the properties of the weld metal in the joint so that the required strength and toughness are obtained. We'll briefly look at the recommended gases for various materials, starting with carbon-manganese steel. Traditionally, carbon dioxide has been used and was replaced by argon-carbon dioxide mixtures. But nowadays, 3-component mixtures of argon, carbon dioxide, and a small amount of oxygen are used. These give a stable arc over a wide range of conditions, and lower spatter levels, and better wetting with smoother, flatter welds than the older gases. For stainless steel, argon-oxygen and argon-carbon dioxide mixtures can be used. But argon-helium mixtures with a small amount of carbon dioxide give better productivity due to a very stable arc with low spatter levels, and clean oxide-free welds, which have excellent weld metal properties which can be produced faster. For welding aluminium, argon can be used for thin sheet, but the addition of helium to the argon gives a hotter arc and is therefore best suited for thicker material. This helium-argon mixture results in good weld penetration and higher travel speeds, once again increasing the productivity.
Right, Mel, shall we go through some of the working practices now, starting first of all with what we wear when we're doing this?
Yeah, welding emits heat plus radiation, so we're wearing flame retardant overalls to protect the skin. In any workshop environment, it's a good idea to wear steel toe cap boots. When we're welding, we're going to be using these stout leather gauntlets, again to protect the hands from heat. We'd always recommend, when MIG welding, to use a head shield. This not only enables you to keep 2 hands on the welding torch, whereas with a hand shield you can't, but also ensures that you do have round-the-face protection against radiation burns. There's a filter at the front. This is selected, determined by the amperage that's going to be used. So for high amperage work, you'd use a darker filter, and for low amperage work where you need to see, you'd have a lighter filter. Welding also emits fumes, so we would recommend the use of local fume extraction.
Right, just like that.
Such as that one. Now, the material itself should always be free from oil or grease. In the case of carbon manganese steel, for very best results, you should clean back to base material. But for practical purposes, you can weld over mill scale or small amounts of rust, as we're going to in this case. The MIG welding process is able to take care of that. Stainless steel and aluminium, however, should always be completely clean. The correct consumables should be selected for the type of material that you're going to weld. And in this case, we have the correct carbon manganese steel wire and the correct shielding gas for this weld.
Okay, Mel, thank you very much for the moment. Well, that brings us to the end of this programme on the process and practice of gas metal arc welding, in which we've looked at the principles of the different transfer modes, the features of the process and its applications. We've looked at some typical gas metal arc welding equipment and explained the preparations required before welding can take place. Right, shall we start off?
We'll do a fillet weld, and I'll do 2.
If you would like a better understanding of welding practice using the gas metal arc welding process, then this is covered in further videos in the BOC series.
Okay, so if you're ready, if you'll mind your eyes as I tack.
You have just seen one of an expanding series of BOC training videos, which cover a wide range of cutting, welding, and safety-related topics. To find out more, call free on 0800 515 661. That's 0800 515 661.